Let's take a look at both number 15 and 16 from section 2.4. This is about projectile motion. On Earth in the absence of air, the rock in exercise 13. That was a question about throwing a rock vertically straight upward on the moon. On Earth, it would reach a height of s equals 24t minus 4.9 t squared meters in t seconds. How high would the rock go? So we're envisioning on the ground a person throwing a rock straight up in the air, and then that rock falling back down to earth. So first it goes up, then it comes down. How high would it go? So really the first thing we want to look for is the point at which it changes direction, or maybe not so much the point first, but when. When does it change direction? When does the velocity go from positive, indicating an upward movement, to negative, indicating a downward movement? So let's figure that out by first finding the velocity function. We know that the position is 24t minus 4.9t squared. The first derivative of that is velocity. So let's use the power rule and get the velocity function to be 24 minus 9.8t. So the velocity indicates to us not only the rate at which the rock is moving, but also the direction which the rock is moving. Positive velocity means up, negative velocity means down. So when does it change? Or in other words, when is the rock at rest? Let's figure out when the velocity is equal to 0. So if we solve this, we'll get negative 9.8t equals negative 24. So t is equal to a 24 over 9.8. Let's let the calculator give us an approximation for that. 24 divided by 9.8. And we see it's about 2.449 seconds. So approximately 2.449. So that's when the rock reaches its high point. But what about what is that high point? What is the position there? In other words, what we want to find is S of the position at 2.449. So let's plug that into the function. We know it's going to be a 24 times 2.449 minus a 4.9 times 2.449 quantity squared. So let's let the calculator do that again. 24 times our 2.449 and then minus a 4.9 times our 2.449 quantity squared. And I see now I've got too many 4s. So let's arrow over and delete one of those. So 24 times 2.449 minus 4.9 times 2.449 quantity squared. Let's hit enter on this. And it's going to be 29.388. So about, what was that one more time? 29.388. And we're in meters here. Meters. How high would the rock go? This. Just about 30 meters in the air. So that takes us to number 16 about a speeding bullet. Bullet fired straight up from the moon's surface would reach a height of s equals 832t minus 2.6 t squared feet after t seconds. On Earth, in the absence of air, its height would reach a position of s equals 832t minus 16t squared feet after t seconds. How long would it take the bullet to get back to the ground in each case? This is less of a calculus problem and more of a pre-calculus or algebra 2 problem. If we think about the ground level, whether it's Earth or the moon, and a bullet being fired straight up, and then it reaches its point of rest, and then it comes back down, we want to know how long that would take. The key here is that at the beginning of this path that the bullet takes going up and then down, the position is 0 in both cases. So really all we need to do here is take the position function, set it equal to 0, and solve. And I think we're going to figure out when that bullet reaches the ground again. So let's start with the moon. The moon. So for number 16, the moon, we know that that position function is 832t minus 2.6t squared. Let's set the position equal to 0. That represents the ground. We know we can factor out a common t. That leaves us with 832t minus, oh, excuse me, there's not a t there anymore. So let's delete these and say 832 minus 2.6 t equals 0. This gives us t equals 0. So the time 0, the bullet is on the ground. Yep, that makes sense. It hasn't been fired yet. What about this one? We want to solve 832 minus 2.6 t equals 0. So that's going to be 832 divided by 2.6. Let's go to the calculator. 832 divided by 2.6 gives us a time of about 320 seconds. Let's put that in. So t equals 320 seconds. And that's how long it takes for the bullet to get back to the ground on the moon. On the Earth, the position function is slightly different. We have 832t minus 16t squared. This is s, the position. We're going to set that equal to 0. Just like the previous question on the moon, we're going to factor out the t. We have 832 minus 16t. So we need to solve both t equals 0. We've got that. And then 832 minus 16t equals 0. So we're going to have t equals, let's go to the calculator, 832 minus 16t. So let's see, back to here, wrong window. Here we are. 832 minus 16, or divided by 16, divided by, there we are, 52. So 52 seconds for our answer there on Earth. So 52 on Earth, 320 on the moon. And there are our answers for number 15 and 16.